Inside every atom of your body, hidden beneath layers of matter, lies a presence we've never directly observed. It's smaller than a proton, stranger than an electron, and yet it forms the very foundation of everything you know. They're called quarks. Think about that for a second. Everything you've ever known is built from atoms. Atoms are made of protons and neutrons, and those in turn are made of these ghostly little things called quarks. They're supposed to be the most basic building blocks of matter. But here's the twist. They don't show up in microscopes. We've never held one in a detector. No photo exists. Still, we believe in them, because the world behaves as if they're real. Protons and neutrons are built from them. Every solid object, every living thing, every star in the night sky, held together by these invisible threads. Pull hard enough on reality, and you end up face to face with these flickering, untouchable pieces of the puzzle. We know they're there, not because we've touched them or trapped them, but because when we smash particles together, we see the traces they leave behind. The energy, the chaos, the patterns. It's like studying the splash of a raindrop long after the drop is gone. Without them, nothing adds up. No stars, no atoms, no you. So what are they really? Are they particles, waves, events, or are they something else entirely? Something that lives on the edge of existence, always just out of reach. And if they can't be seen, touched, or separated from the things they build, can we still call them real? Because if quarks aren't real, what does that make you? This isn't just a science question. This is a reality-breaking, mind-warping question that shakes the foundation of everything we think we know. You're told the world is made of matter, of atoms, of particles too small to see. But what if the truth is, we've never actually seen the most important ones? Quarks are supposed to be the building blocks of everything. They're what make up protons and neutrons, the core of every atom in your body, in your food, in the stars. They're everywhere, and yet no one has ever seen a quark by itself. Not once, ever. So here's the question. How can something so essential to reality be completely invisible? What are you supposed to believe when the very ingredients that make up your body don't show up in any detector? Why is the universe hiding them? Scientists have tried. We've built billion-dollar machines. We've smashed atoms together at near light speeds. We've torn apart matter hoping to find just one lonely quark, and every single time, it slips away. Why? Why do quarks refuse to be alone? Why do they always vanish into new particles the moment we try to isolate them? Why does the force holding them together get stronger the more we try to pull them apart? And here's the strangest part. Even though we've never caught one, the universe behaves exactly as if quarks are real. The math works. The predictions work. Every ripple, every reaction, every collision points to something we can't see, can't touch, can't isolate. So, are they real? Or are they just convenient fiction? Rules written into nature's code to make everything look like it fits? And if they are real, then what else might be hiding, just out of reach? Today, we're not just asking what a quark is. We're asking something bigger. What does it mean to exist if the most fundamental parts of you never show their face? Because this isn't just about particles. This is about you, and the question of whether you are real in the same way that quarks are, or aren't. The lie of solidity. Let's start with something simple. Look at it. Move your fingers. Touch your palm. It's real, right? Solid. Tangible. You can clench it into a fist, feel its weight, and press it against a table. There's no doubt it's there. But now, let's go deeper. Not metaphorically, literally. Let's peel back the surface, not the skin, not the muscle, not the cells, but far beyond that. Let's shrink ourselves down 1,000,000 times, then 1,000,000,000. Now keep going. Eventually, we'll reach the world of atoms. And here's where everything you think you know about your hand starts to unravel. Atoms make up everything. You, me, the table, the stars. But an atom isn't what most of us imagine. It's not a tiny ball. not a mini solar system. It's mostly nothing. If you were to scale up a single atom so that its nucleus was the size of a peanut, the nearest electrons would be orbiting over a football field away. And in between, nothing. Just space. Vast, silent, invisible nothingness. Your hand, your body, the solid things you trust every day, they're illusions of contact. When you tap your finger on a desk, nothing touches. What you're feeling is the electromagnetic repulsion between the clouds of electrons. Matter pushes against matter, but nothing ever truly meets. So what does that mean? If everything's made of atoms, and atoms are mostly empty, then everything is mostly empty. You are mostly empty. That's not poetic, that's physical reality. And it gets stranger. Let's take a closer look at that atom. At its heart lies the nucleus, dense, minuscule, and packed with protons and neutrons. These are the solid bits that give atoms their mass. But even these aren't indivisible. They're not the end of the story, because inside each proton and neutron, there's something even smaller, something more fundamental: quarks. These are some of the most basic building blocks of reality. As far as we know, quarks don't have any internal structure. They just are. Each proton in your body is made of 2 up quarks and 1 down quark. Neutrons are 2 downs and 1 up. That's it. Those combinations define the building blocks of atomic nuclei. They're held together by a kind of glue that makes duct tape look like child's play. The strong nuclear force carried by particles called gluons. Now, this is where things get bizarre. Try to pull a quark out of a proton. Go ahead, stretch it, and instead of the force weakening, like a stretched rubber band, it gets stronger. Keep pulling, and at some point, you won't be able to separate them. You'll just have to settle for creating a brand new pair of quarks. It's like trying to cut a magnet in half and ending up with 2 magnets, each with a new north and south pole. Nature refuses to let you isolate a single quark. No one has ever seen a lone quark in the wild, not because we're not clever enough, but because the universe won't allow it. It's as if quarks have made a pact. We stay together, or not at all. And that raises a question. If the things we call particles are never really alone, what are they? Are they truly particles, or just disturbances, vibrations, temporary events in a deeper field? What exactly is this stuff we're made of? It's tempting to think of particles as tiny billiard balls, bouncing around in the void, but quantum physics killed that illusion a long time ago. Electrons, for instance, don't orbit the nucleus like little planets. That old image, while charming, is wrong. Electrons exist in a kind of cloud, a haze of probability. They have no definite location until we try to look. They're not anywhere specific, and yet they are. Everywhere and nowhere, all at once. When you observe an electron, it behaves like a particle, but when you're not watching, it behaves like a wave. Which one is it really? We don't know, and maybe that's the wrong question. Maybe it's not that the universe hides its truth from us, but that our language just isn't equipped to describe it. Words like solid, particle, and thing may work in the macroscopic world, but they fall apart down here, and so do our intuitions. Imagine if, instead of atoms being full of matter, they were like tiny vibrating notes on an infinite string. That's one of the ideas behind string theory, that everything from quarks to electrons to you and me is made of tiny oscillations of energy, resonating in dimensions we can't see. Not particles, not marbles, not even clouds, just music, vibration. And perhaps that's closer to the truth than we think, because when you look deep into matter, the solidity fades away. What's left isn't stuff, it's relationships, fields, forces, interactions. The universe isn't made of things, it's made of processes. Now ask yourself, if your hand is mostly empty, and the stuff inside it is more like potential than presence, what does it mean to be real? That's not just a physics question, it's a philosophical one. Because when we realize that solidity is an illusion, that mass is a trick of motion, that form is a ripple in a field, It shifts how we understand everything. You're not a collection of objects. You're a pattern in space-time, a living, breathing wave in the cosmic ocean. And even more humbling, this dance of particles and forces, the same stuff that forms black holes and galaxies, is what gives rise to your thoughts, your memories, your sense of self. Somehow from quarks and electrons, these ghostly, intangible ingredients, emerges the feeling of being you. What part of that is solid? Is your identity a thing or a flow, a snapshot or a film? Physics doesn't have all the answers. It's honest about that. The more we learn, the stranger it gets. Reality doesn't become clearer, it becomes deeper. The questions get bigger and more personal. Because when you discover that matter isn't really matter, you can't help but wonder, what is real? The table you touch, the coffee you drink, the voice in your head, they're all patterns in a sea of uncertainty. Your very existence is a ripple in a quantum field, briefly rising, then falling back into silence. But don't let that scare you. Let it awaken you. Because if everything is made of the same strange fabric, if there's no firm ground beneath us, then we are, in a very real sense, part of a cosmic story, woven from the same threads as stars. The illusion of solidity may be just that, an illusion, but it's a beautiful one that lets us build cities, hold hands, hug loved ones, paint, dance, write, and wonder. The real mystery isn't that we're mostly empty space. The mystery is how that emptiness becomes meaning, how nothing becomes everything, and that, perhaps, is the greatest truth hidden inside your hand. Why we think they're real, even though we've never seen one. It's one of the strangest truths in modern science. The more deeply we look into the heart of matter, the less solid anything we actually find. We chip away at the building blocks of reality, expecting to hit bedrock eventually, something final, something indivisible. But every time we dig deeper, the bottom seems to fall away again. And then we hit quarks. Or rather, we didn't. We've never seen a quark. Not once. Not directly. No photo. No video. No trail on a screen. Not even the ghost of a footprint in a detector. And yet, we are nearly certain they exist. Think about that. We're talking about the fundamental ingredients of everything you've ever touched, tasted, held, or been. The atoms in your bones, the protons and neutrons at the core of those atoms. Each one of them is made of quarks, but no one has ever held a quark in their hand, or even in their microscope. And still, we believe. Not because of faith, but because of something even more mysterious. Consistency, predictability. A universe that, when poked in just the right way, responds with math that points squarely at the invisible. Let's start from the beginning. Physicists weren't trying to prove quarks existed. In fact, for a long time, the idea of things being made of smaller things was already getting exhausting. Electrons, protons, neutrons, great. That seemed like enough. Why mess it up with more? But nature had other plans. In high-energy experiments, when scientists began smashing particles together at near-light speeds, trying to recreate conditions close to the Big Bang, they noticed something strange. The pieces that came flying out didn't behave like simple debris. Instead, they arranged themselves in patterns, not just once or twice, but over and over, with uncanny regularity. New particles popped into existence, but always with familiar properties, masses and charges that seemed to obey an internal structure, like puzzle pieces that hinted at a bigger image just out of reach. It was as if we were breaking open a watch and seeing gears, springs, and cogs inside, but never being able to pull one out to study it. The patterns were too perfect to be a coincidence. So theorists started building a model. What if protons and neutrons weren't the end of the line? What if they too were made of smaller entities? Quarks, tiny twitching fragments of energy, coming together in triplets or pairs to build everything else. And here's where it gets surreal. The math just worked. Suddenly, chaos became order. Particle masses that had been confusing now made sense. The way particles decayed into others, their lifetimes, spins, magnetic moments, decay paths, all of it lined up if you assumed quarks were real. But there was a catch. You couldn't isolate one. Every time you tried to knock a quark free, the universe would slam the door shut. It's called confinement, a beautifully frustrating rule of quantum chromodynamics, the theory that governs quarks, and the strong nuclear force. The harder you try to pull a quark out, the more energy you pump in. But that energy doesn't buy you freedom. It just spawns more particles. Tug hard enough, and instead of getting a single liberated quark, you get a pair. The leash snaps back, but it snaps with a friend. Imagine trying to separate two magnets connected by a rubber band. The farther you pull them apart, the tighter the band stretches. But instead of breaking, the band just creates a new magnet in the middle. Now you've got two pairs, still no solo flyer. And so, quarks remain permanently caged. But here's the mystery. Even if we've never seen a quark, we feel their presence everywhere, like ripples on a pond. You don't need to see the stone that caused them to know something sank. The ripples carry the fingerprint of the object, its size, shape, mass, and speed. You can reverse engineer the splash. That's what we've done with quarks. We build colliders, smash particles, analyze the debris, and over, we see traces, subtle, consistent, undeniable, of hidden architecture. And not just structure, but beauty, symmetries, patterns that are so elegantly woven, they almost feel intentional. It's like discovering the ruins of a vanished city by the regular spacing of the stones. You didn't see the builders. You never met the civilization. But the order is too precise. The design is too familiar. Now pause here. This is where it gets philosophical. What does it mean to know something exists? Is it sight, touch, direct experience? Or is it something deeper, something abstract, yet just as real? We've never seen gravity either, not directly. We've never caught a graviton in a bottle. And yet, every step you take is a conversation with it. Every falling apple, every orbiting moon. We've never seen consciousness, never opened a brain and found the self. And yet here you are reading these words, feeling them, thinking about them. Something is undeniably there. Reality is slippery. We're so used to trusting our senses that we forget how often they lie to us. Our eyes can't see ultraviolet. Our ears can't hear ultrasound. Our skin can't feel individual atoms. And yet, all of those things exist, provably, reliably, repeatably. The universe is under no obligation to make itself obvious. The deeper we go, the more abstract it becomes. At macroscopic scales, we have chairs, trees, and people. At the atomic level, we have protons and electrons, probability clouds, more than things. At the quantum level, we have excitations and fields. And somewhere deep inside that quantum fog, quarks, elusive, enigmatic, and utterly essential. You can deny a unicorn because it's a mashup of familiar creatures, a horse, a horn. But you can't deny a quark because without it, the universe falls apart. Without quarks, nothing we observe would behave the way it does. Without quarks, atoms wouldn't hold together, stars couldn't burn, neutrons couldn't decay. There would be no periodic table, no chemistry, no you. All of that hinges on something we've never seen. That feels like a contradiction, but it's the heart of science. Science isn't just about observation, it's about inference, about building bridges between what we know and what must be true to make the known possible. We don't believe in quarks because we want to. We believe in them because the universe behaves as if they're there, repeatedly, predictably, elegantly. And yet the idea that the deepest truths are invisible, that the universe runs on software we'll never directly access, can be unsettling. There's a kind of loneliness in that, a cosmic humility. Imagine knowing that every cell in your body is made of swirling storms of particles, that themselves are made of components we can never touch. You are a living cathedral, built from bricks that will never stand alone. But maybe that's part of the wonder. Quarks remind us that reality isn't built for our convenience. It's not made to fit neatly in our instruments or our instincts. It's far stranger, deeper, and more elusive than any story we could have invented. And yet somehow, we can still grasp it, not by seeing, but by understanding. In a way, quarks are like the soul of matter, hidden, essential, intangible. You can't put your finger on them, but take them away, and the whole structure collapses. They also raise deeper questions. If quarks are real but forever out of reach, what else might be? Are there other layers beneath them? Other truths we've only scratched the surface of? Is the universe infinitely divisible? Or will we someday hit the final pixel of reality, the true bottom? And what does it say about us that we can even ask? Somewhere between atoms and galaxies, between neurons and nebulae, we evolved minds that could unravel these mysteries, minds that can accept invisible truths, minds that can build machines to glimpse the unglimpsable. Maybe the fact that we've never seen a quark isn't a limitation. Maybe it's a lesson. Maybe it's a lesson. That truth doesn't have to be visible to be real. That not everything important shows up on a screen. That the deepest parts of the universe, and perhaps of ourselves, can only be known through their effects. We see the ripples, we hear the echoes, we feel the gravity, and that is enough. The strange history of quarks. In the early 1960s, physicists were facing a problem that felt strangely familiar. Too much information, and no idea what to do with it. Their blackboards were cluttered with names. New subatomic particles were appearing almost faster than anyone could study them. Pions, kaons, mesons, baryons. It felt like the universe had turned into a cosmic junk drawer, filled with mysterious bits and pieces that didn't seem to follow any rhyme or reason. The more they searched, the messier it got. The so-called particle zoo had grown into a full-blown circus. It was exciting, yes, but also deeply unsettling. Scientists weren't looking for chaos. They were looking for order, for some underlying simplicity that could explain why reality was the way it was. And right then, reality seemed to be laughing at them. Enter Murray Gell-Mann. He wasn't just a brilliant physicist. He was the kind of thinker who could look at a storm and notice the shape of the wind. Where others saw a pile of scraps, he saw a hidden pattern, like constellations traced in a sky full of stars. And he had a radical idea. What if all these strange new particles weren't truly fundamental? What if they were made from something even smaller? What if the universe, in all its elegance and confusion, was built not from dozens of building blocks, but just a few? It was a dangerous kind of thinking. It meant challenging the way physicists had been seeing things for years, but it also felt right. The best ideas often do, not because they're easy, but because they make everything else fall into place. So Gell-Mann gave these invisible ingredients a name, quarks. Not because it sounded technical, not because it was rooted in Latin or Greek, like most scientific terms. No, quark came from a bizarre, dreamlike line in James Joyce's Finnegan's Wake. 3 quarks for muster mark, pure literary nonsense and yet strangely perfect. Because these particles weren't just strange, they were unknowable, unseeable, more like whispers in the equations than things anyone had ever actually observed. But Gell-Mann's hunch paid off. When you looked at the so-called particle zoo through the lens of quarks, the noise began to resolve into music. Protons and neutrons weren't mysteries anymore. They were combinations. 3 quarks bound together. Mesons? Just pairs of quark and antiquark. Suddenly the patterns emerged like a secret language hidden in plain sight. The chaos had a grammar. 3 types of quarks, up, down, and strange, were enough to explain nearly everything they'd seen. Later, more would be discovered. Charm, bottom, and top. But the foundation had been laid. It was one of the most important breakthroughs in modern physics. But here's the strange part. No one has ever seen a quark. Not then, not now. Not even with the most powerful particle accelerators on Earth. We can smash protons together at near light speed. We can crack open the building blocks of matter. But no matter how hard we try, We never catch a quark flying out into the void on its own. They're always confined, bound so tightly together that pulling them apart doesn't separate them. It just creates more quarks, like stretching a rubber band that snaps and forms new pieces rather than breaking. It's called quark confinement, and it's one of the most bizarre features of our universe. You can't isolate a quark. You can only infer it. Its existence is more mathematical than material, more whisper than shout. It's real because the math says it must be. It explains things we can measure and predict, but no one's ever held one. No one's ever seen one directly, not even close, which raises a deeply uncomfortable question. What does it mean for something to be real? If you can't touch it, see it, or hold it, if it exists only in equations and indirect evidence, does it belong to the physical world or to the world of ideas? Are quarks real in the same way a rock is real? Or are they more like the concept of justice or infinity, true in some higher, abstract sense? This is where physics starts to lean into philosophy. The deeper we look into the fabric of matter, the more it begins to behave like a shadow cast by something beyond our grasp. We thought we were peeling back the layers of the universe to find something solid, something fundamental. But instead we keep finding patterns, relationships, probabilities, stories really. And every time we think we've reached the bottom, there's another layer waiting. Quarks, in a way, are reminders of the limits of human perception. They're the ghosts that structure reality. We don't see them, but without them, nothing would exist. No atoms, no stars, no life. They are the silent architects of matter, and yet they don't want to be seen. It's as if the universe is telling us, you can know that I exist, you can learn my patterns, but you will never touch my deepest truths. That's both beautiful and unsettling. There's a kind of humility built into this story. We like to imagine ourselves as masters of the universe, unlocking the secrets of nature like puzzle boxes. But the story of quarks reminds us that knowledge doesn't always mean visibility, that some truths aren't on display. They hide in the gaps, in the symmetry, in the structure behind the scenes. And maybe, just maybe, that's what makes them matter. The rules of the game. There's a rule buried deep in the heart of reality, one that not even the wildest corner of the cosmos dares to break. It's not written in stone or whispered by gods. It's etched into the fabric of existence, a silent commandment the universe obeys without exception. No quark ever walks alone. They come in twos or threes, always. Like cosmic secret keepers, they huddle together, never letting one slip away into the open. You could chase them with the most powerful particle accelerator on Earth, throw unimaginable energy at them, try to yank them apart, and still, they won't let go. Because if you try, nature doesn't just say no, it retaliates. The more you pull, the harder it pushes back. It's as if reality itself resists your curiosity, your desire to see what a single quark looks like on its own. But instead of snapping like a rubber band or surrendering under pressure, something stranger happens. The tension you create doesn't tear the pair apart. It tears the vacuum instead. And out of that shredded emptiness, new quarks are born. Not so you can finally observe one in isolation, but to restore the group. The universe doesn't give you what you asked for. It gives you more of what you tried to separate. This strange, almost poetic defiance has a name. Physicists call it confinement, but it feels like something older than physics, like a principle of balance, like a cosmic metaphor hidden in plain sight. No one truly exists alone. But what enforces this rule? What holds these quarks together so fiercely that even a direct assault only results in more connection? The answer is almost mythological in its intensity. The strong force. The strongest of all the fundamental forces. Not just stronger than gravity, billions of times stronger. Not just stronger than electromagnetism, vastly more stubborn. It's the unshakable grip at the center of matter, the invisible hand that shapes everything from the nuclei of atoms to the iron in your blood. But strength alone isn't what makes it fascinating. What makes it truly alien almost spiritual in its paradox, is that it grows stronger with distance. Imagine trying to separate two objects only to discover that the farther apart they get, the more fiercely they're pulled back together. That's not how we're used to thinking about forces. Gravity weakens as planets drift apart. Magnetism fades. Even light gets tired after traveling for billions of years. But not the strong force. It does the opposite. It tightens. It resists. It clings. It's as if the universe is saying, these things belong together. And yet, we've never seen the thing it's protecting. We've never captured a lone quark in any detector, never glimpsed one in isolation, never watched it wander off like a curious child from a crowded park. Every time we've tried, nature's answer has been the same. You don't get to see this. So what exactly is this force? What gives it this unbreakable grip? The answer is almost as strange as the question. Gluons. Yes, gluons. Tiny massless particles with the most thankless job in the cosmos, holding everything together. They're the mediators of the strong force, the messengers between quarks. But they're not like the other force carriers you may have heard about. Photons, which carry light, are polite. They don't get involved with each other. Gravitons, if they exist, quietly transmit gravity without making a scene. Even the W and Z bosons, responsible for radioactive decay, keep their distance, but gluons, they're chaotic, rebellious, unruly. They interact with each other, constantly. They don't just deliver the message, they tangle themselves up in it. Gluons stick to other gluons, creating a kind of infinite knot, a feedback loop of connection. It's like sending a courier who tapes themselves to the letter they're carrying, then grabs the next courier, and the next. It's this feedback, this self-binding nature that turns the strong force into an unbreakable prison. It's not just that quarks are chained together, it's that the chains are alive. If you could shrink down small enough, smaller than atoms, smaller than protons, smaller even than the space between quarks, you wouldn't find emptiness. You'd find tension, fields, pressure, and at the center of it all, a storm of gluons knotted into a relentless whirlwind, anchoring the quarks in place, not with stillness, but with turbulence. We call this storm a hadron, a name for the particles built out of quarks and gluons. Protons and neutrons are the most famous hadrons. They make up nearly all the visible matter in the universe, and they only exist because of this furious confinement, because of a force that refuses to let go, that refuses to show us the pieces. It's almost like the universe is playing a game, a deep game. It is one that challenges your understanding, not just of physics, but of freedom, of identity, of separation. Why does the universe insist that certain things stay together? We don't really know. Is it because something terrible would happen if they came apart, or something beautiful? Or is it simply the structure of the game board, rules with no reason, just order for the sake of order? There's something oddly human in all this, a kind of spiritual symmetry. We long to be independent, to understand ourselves fully, to stand alone and say, this is what I am. But we're never really alone, are we? We're held in place by forces we can't see, memories, relationships, gravity, time. And the more we try to isolate ourselves, the more the world seems to push back, reminding us that identity is entangled, that nothing, not even a quark, can escape its context. Some physicists have tried to simulate what a free quark would look like. They've built models, run equations, imagined the possibilities. But all of it feels like trying to draw a color that doesn't exist, because in every real attempt to liberate a quark, we only ever make more hadrons. We can't even break them apart. We can only multiply the whole. It's tempting to think of this as failure, that nature is hiding something from us, that if we could just push harder, we'd finally get the answer. But maybe it's not failure. Maybe it's the answer. Maybe the truth isn't found in the pieces, but in the bonds between them. Maybe what matters is not the quark, but the gluon, the relationship, the tie, the invisible line between two things that keeps both of them real. That's what confinement is. Not just a physical phenomenon, but a philosophical one. A reminder that isolation is an illusion, that even the smallest building blocks of matter are not solitary dots but shared patterns, networks, companions in a dance older than time. And perhaps that's why we find beauty in connection, in friendship, in love. Maybe we're echoing something deeper, something baked into the very structure of the cosmos, the idea that wholeness is more fundamental than individuality, that freedom doesn't come from escaping the bonds, but from understanding why they exist. So next time you look in the mirror, remember, the particles you're made of, the protons in your atoms, the quarks inside those protons, aren't just clumps of stuff. They're locked symphonies, held together not by choice but by necessity, not wandering souls but communities, bound endlessly by the strongest force in the universe. And maybe, just maybe, so are we. Not things, but ripples in fields. There's a quiet moment, late at night, when the world settles just enough for your thoughts to stretch out and drift. Maybe you've had one of those moments, when the stars feel impossibly far, and yet, for some reason, you can't shake the feeling that you're somehow entangled with them. Not just metaphorically, literally, like there's something beneath all this skin and bone and breath that connects you to the fabric of the cosmos. This is where things start to get weird. You've probably been told, at some point, that you're made of atoms, that those atoms are made of even smaller pieces, protons, neutrons, electrons. Maybe you remember that those protons and neutrons are made of something even smaller still, quarks. Tiny building blocks like the Lego bricks of reality, stack enough together and you get you. But that picture, while comforting in its simplicity, isn't quite true. Because in the deepest, most precise theories we have about how reality actually works, those so-called building blocks aren't blocks at all. They're not things. They don't sit in space like little marbles waiting to be assembled. According to quantum field theory, the strange, elegant framework that underpins our understanding of particles and forces, those particles aren't objects, they're ripples, temporary disturbances in invisible fields that fill the universe. Imagine throwing a stone into a still pond. The stone disappears beneath the surface, but the ripples remain for a while, expanding outward, subtle but undeniable. That's what an electron is. Not the stone, but the ripple. Not a chunk of matter with edges and a center, but a flutter in an all-pervading field. There is, quite literally, an electron field stretching through all of space, everywhere. Right now, it passes through you, through your phone or computer, through the ground beneath your feet. That field is always there. And an electron, any electron, is simply a vibration in that field, a brief event, a kind of note played by the cosmos. The same goes for every other particle. A photon, the particle of light, is a ripple in the electromagnetic field. Quarks, those tiny constituents of protons and neutrons, are flickers in the 6 distinct quark fields. Even the Higgs boson, which famously gave mass to other particles, is a ripple in the Higgs field. Reality, in this view, isn't built out of bits of stuff. It's a concert of fields humming and resonating, and everything we call a particle is just the music. Let that sink in. You are not made of things. You are made of happenings. The atoms in your body, each nucleus, each proton inside that nucleus is not a little nugget of substance. It's a swirling, buzzing chaos of quantum events, fields dancing with each other, balancing, exchanging energy, flirting with uncertainty. What you think of as solid is just a sustained pattern of interactions. And here's the real kicker. The mass, the weight, the substance of a proton doesn't actually come from the quarks inside it. Not most of it anyway. You'd think it would. After all, quarks are supposed to be the pieces that make protons, right? But when physicists run the numbers, something astonishing happens. The 3 quarks inside a proton, 2 up quarks and 1 down quark, contribute less than 2% of its mass. That's it. The rest, the other 98%, It comes from energy, from motion, from the relentless jittering dance of those quarks, constantly interacting through the strong force, held together by particles called gluons. It comes from the energy of confinement, from the pressure and turmoil and kinetic buzz inside that quantum prison. The mass that lets you stand, move, think, exist. It's not stuff. It's energy caught in a pattern. It's the quantum equivalent of a storm system, maintained not by matter, but by movement. You are, in a very real way, a bundle of organized chaos, a temporary beautiful resonance in an ocean of invisible fields. And yes, this means that most of what you are comes from nothing. Not nothing in the ordinary sense, an empty room or a blank page, but quantum nothing. The kind that's never truly empty. The vacuum, in quantum field theory, isn't still. It seethes, it fluctuates, it bubbles with potential. Particles appear and disappear. Fields pulse with energy, even in their lowest possible state. It's a storm beneath calm waters. You, me, everything we touch, all of it arises out of this quantum vacuum, out of absence itself, being from non-being. That's not just poetry, it's physics. And yet, it feels like poetry, doesn't it? There's something deeply unsettling about this view of reality, and something deeply comforting. You're not made of objects, you're made of interactions. Your body, your thoughts, your memories, all ripple effects, playing out for a while in this vast quantum sea. We like to think of ourselves as separate from the universe, as individuals, bounded, distinct. But quantum field theory says otherwise. It says we're embedded in the fields that weave through everything, that the particles that make us aren't our own, really. They're events in shared fields. You aren't merely in the universe, you are of it. Sometimes this can feel alien, cold, like we're nothing more than physics equations acting themselves out. But look closer. There's an intimacy to it, a unity. Because if all electrons are ripples in the same field, then every electron, whether it's in your hand, your heart, or a star a billion light years away, is, in a way, the same thing. Not just similar, identical, indistinguishable. Each one is a note played on the same universal instrument. That's wild, and it's humbling. It means you don't just share a history with the universe, you share an identity. The particles that make you didn't come from somewhere else. They didn't migrate into your body. They're not visitors. They are you, but they're also not yours. They're local expressions of something far larger, something that doesn't belong to anyone, because it is everything. And this raises a strange question. If all particles are ripples in fields, what are you? Not just biologically, philosophically. If there's no fundamental stuff, if all of existence is just organized energy, dancing to the tune of invisible laws, then where do you begin and end? Are you your atoms? They're not fixed. You inhale new ones every second, shed old ones constantly. In 7 years, almost every atom in your body will have been replaced. Are you your particles? They're not really yours. They're temporary, just flickers. Are you the pattern then? The structure that persists while the components change? Maybe. Maybe you are a kind of ripple too. A ripple in time. A self-aware pattern held together long enough to wonder where it came from, to feel joy and fear and love, to ask questions about its place in the cosmos. That's not nothing. In fact, that might be everything. Because it means the universe isn't just vibrating. It's listening to itself, asking about itself. You, a ripple in quantum fields, are somehow conscious, somehow aware, a part of the universe that's awake. And maybe that's what makes it beautiful. Not the particles, not the mass, but the mystery, the fact that we don't fully understand how this all works, that we can model it, mathematically, with precision, and still be struck dumb by the implications, that we can send machines into space and smash particles in giant rings, and yet sit quietly at night, staring at the stars, wondering what it all means. You're not a thing, you're a happening, a brief, miraculous event in a universe made of questions. And maybe the point isn't to find all the answers. Maybe it's just to marvel that you're here to ask. Exotic beasts. When quarks get weird. You probably grew up hearing about protons and neutrons, maybe in a classroom with a poster of the periodic table, or a science book showing colorful spheres labeled atoms, tiny building blocks of matter, neat, self-contained, easy to visualize. But the truth is far stranger and infinitely more beautiful, because deep inside those familiar particles, inside every atom of your body and every star in the sky, there's a chaos of shifting forces, a dance of energy and motion, held together not by shells or walls, but by rules written in the strange, silent language of quantum physics. And at the heart of that dance are the quarks. Quarks are elusive. They're not things you can point to, like a rock or a planet. You never see a quark alone. They don't like to be isolated. Whenever scientists try to separate them, the energy from that effort just creates more particles, more quarks. It's like trying to tear a drop of water from the ocean, only to find it growing new waves around your hand. So instead, quarks are always found in groups, usually 3 of them. The classic proton, the classic neutron. That's the tidy version most of us learned first. But that's not the whole story. Far from it. Under extreme conditions that barely exist naturally anywhere in the modern universe, quarks begin to behave in new ways. They team up in strange, unstable combinations like a jazz band, improvising in a style no one's heard before. And sometimes, for a brief moment, they reveal something ancient and alien, a deeper pattern in the quantum sea. In 2003, something happened that shook the foundation of our understanding. It was subtle, easy to miss if you weren't watching carefully. Scientists at the Bell experiment in Japan were smashing particles together at unimaginable speeds, trying to crack open nature's hidden layers. And in the debris, they found something weird, a new particle that didn't fit. This particle, later named X3872, had a mass that didn't match any known configuration of 3 quark particles. It didn't fit the playbook of protons and neutrons, or even the well-studied mesons, which are made of just 2 quarks, a quark and an antiquark. This thing had 4, not 2, not 3, 4. 1 charm quark, 1 anti-charm, 1 up and 1 anti-down, a tetraquark. For decades, physicists had wondered if such a thing could exist. The math said yes, the standard model allowed it, but no one had ever seen one. And then, suddenly, it was there. A particle made of 4 quarks. Real, observable, confirmed. Not just a theoretical sketch on paper, but an actual creature in the quantum zoo. That discovery cracked open the door to a whole new layer of reality. Because if tetraquarks were possible, what else might be out there? What other combinations of quarks were waiting in the wings, unseen? The answer came swiftly. Just over a decade later, scientists at CERN found something even wilder. A particle made of 5 quarks, a pentaquark. This time it was a beauty of complexity. 3 quarks and 2 antiquarks, swirling in a fleeting, unstable alliance. Like a temporary alliance of nations in a time of chaos, the pentaquark forms, holds itself together for a tiny blink of existence, then collapses into something simpler. It's hard to describe how strange that is. These aren't molecules. They're not atoms. They're not even the particles that make up atoms. There's something deeper, more fundamental, and more chaotic. They appear only under precise, high-energy conditions and vanish almost instantly, like mirages at the edge of reality. But we've seen them. We've measured them. They are real. And the implications are staggering, because these exotic particles aren't just curiosities. They hint at a whole unexplored territory within the quantum realm, an ocean of possible arrangements and forces, of symmetries we haven't mapped yet, and maybe never will fully understand. They tell us that matter, at its most basic level, isn't static or final. It's experimental. It's playful. It tries things out. You start to wonder, if these strange particles can exist in the lab, could they exist elsewhere? Naturally. Could the universe have cooked up its own exotic quark formations in the extreme furnaces of cosmic history? Well, maybe it already has. There's a hypothesis, bold and chilling, that in the densest places in the universe, in the hearts of dying stars, something utterly alien is born. Not black holes, not neutron stars, but something stranger, quark stars. Now, to grasp just how bizarre this idea is, imagine what happens when a massive star collapses under its own gravity. If it's not big enough to become a black hole, it turns into a neutron star, a hyperdense ball of neutrons crushed so tightly that a single teaspoon of it would weigh 1 billion tons. Already, that's hard to wrap your head around. But what if the pressure goes even further? At some unimaginable point, the neutrons themselves, those familiar trios of quarks, get squeezed so hard that they dissolve. They break apart into a sea of free-floating quarks, not bound, not grouped, just a quantum liquid of pure quark matter, a star that's not made of atoms, or ions, or even neutrons, but quarks, free and flowing. No surface, no structure, just a vast, dense ocean of the stuff that all other matter is made from, like peeling back the layers of a planet and finding only the core, no crust, a core that pulses and shifts, held together not by chemical bonds, but by the raw force of the strong nuclear interaction, the most powerful force in the universe. Quark stars, if they exist, would be darker and denser than anything we've ever directly observed. We wouldn't see them in the traditional sense, but we might catch their gravitational fingerprint, maybe in the odd behavior of binary systems, or in the precise timing of pulsars, or in the eerie remnants of supernova explosions that don't quite add up. We haven't confirmed one yet. Not fully, but the idea refuses to go away, because it fits, not just with the math, with the logic, with the rhythm of how the universe operates. Every time we think we've reached the bottom, quarks, gluons, the standard model, the floor creaks beneath us. Something deeper stirs. A new layer reveals itself. Reality keeps showing us that it's not made of solid blocks, not clean lines and stable parts. It's a process, a flux, a continual becoming. Quark matter is just the next chapter in that unfolding story. And the weird part? All of this is you. The quarks that make up tetraquarks and pentaquarks and possibly entire stars, they're the same kind that make up your body, your blood, your thoughts. The difference isn't what they are, it's how they're arranged, how they combine, the patterns they choose. You are a pattern in the chaos. That's maybe the most humbling realization of all. The universe doesn't build itself from stuff the way we usually think of stuff. It builds from relationships, from interactions, from moments where particles meet, bind, fall apart, and recombine, like music emerging from vibrations, like meaning emerging from words. What then are we? Not things, not objects, but resonances, temporary configurations of energy and form. And somewhere out there, in the darkness between galaxies, there might be stars living that truth in a more literal way than we ever imagined. Stars that don't burn or shine in the way we know, but pulse with pure quark matter, the deepest note in the cosmic song. It's unsettling, it's thrilling, and it leaves you wondering what else might be out there, not in the far reaches of the universe, but right here, beneath our feet, hiding in plain sight, waiting for the right pressure, the right energy, the right question to burst forth in a new form. Because when quarks get weird, reality itself changes shape. And maybe that's the secret. The universe isn't a place of things at all. It's a place of surprises. Entanglement, quarks that stay connected. In 2021, something strange, something quietly astonishing, happened deep underground in the sprawling tunnels of CERN. Amid the roar of high-speed particles and magnetic fields twisting like invisible whirlpools, physicists made a discovery. Not the kind that makes headlines in the usual way, not a new particle, not a shiny new theory, but something more subtle, more haunting. Two quarks, specifically a top quark and its antimatter twin, were created in the heart of a high-energy collision. Born from the same violent moment, they spun away from each other into opposite directions. And yet, in some way that defies common sense, they remained connected, not by wires, not by forces, but by something far more mysterious: quantum entanglement. Their properties, specifically their quantum spins, were not just similar, they were entangled, meaning when one changed, so did the other. Instantly, as if they were still part of the same system, though space itself had stretched between them, as if distance didn't matter. And just like that, something profoundly old and deeply strange reminded us it's still lurking at the heart of reality. Entanglement isn't new. Physicists have known about it for nearly a century, ever since Einstein grumbled about spooky action at a distance, and Niels Bohr countered with a shrug and a smile. It's a core part of quantum mechanics, but seeing it in top quarks, a particle so massive it decays faster than anything else we know, is like seeing lightning frozen in midair. It's rare, it's brief, and it forces us to ask uncomfortable questions. Because if something like a top quark, a particle that blinks into existence and vanishes in less than a trillionth of a second, can be entangled, then what else can? And more unsettling still, what is entanglement really? It's easy to describe, harder to believe. When two particles become entangled, they don't just share information, they become one system. No matter how far apart they drift, their properties remain tied together. Measure one, and you instantly know something about the other. There's no signal traveling between them, no secret message passed back and forth. It's not communication in the way we understand it. It's more like coordination, a synchronicity written into the fabric of the universe itself. Now pause for a moment and let that sit, because here's the part that starts to feel almost mythic. There is no upper limit to how far entanglement can stretch. It doesn't weaken with distance, a meter, a mile, a million light years. It doesn't care. Once entangled, always entangled, at least in principle. So when quarks, these fundamental building blocks of the universe, display this behavior, we can't help but wonder, could it be happening elsewhere? Could it be happening here? After all, you're made of quarks too. Protons and neutrons at the core of every atom in your body are made of quarks glued together by fields we don't experience directly. Every thought you've ever had, every breath you've ever taken, has involved quarks dancing through space and time, obeying rules no human fully understands. So the question arises, and it feels like it's whispering just behind your ear. Is it possible that some part of you is still entangled with something else? Maybe with another particle, maybe with another person, maybe with a piece of the universe so far away, you'll never even know it exists. We don't know. But the question won't leave. And it gets deeper. Because entanglement doesn't just challenge our understanding of particles. It challenges our understanding of reality. It forces us to reconsider what we mean when we say two things are separate. If you and I are entangled, not metaphorically but physically, then where do I end and you begin? This isn't science fiction. It's quantum physics, tested in labs, confirmed in equations, and now witnessed in the most fleeting of particles at the edge of detection. But the implications stretch far beyond the lab. Imagine this. Somewhere in the early universe, moments after the Big Bang, two particles were born from the same burst of energy. They shot off in opposite directions as the universe expanded around them. Billions of years passed, stars formed, planets coalesced, life arose, and one of those particles, by some cosmic lottery, ended up in you. The other? Maybe it's still out there, buried in the heart of a distant star, or floating through the dark between galaxies, or maybe it blinked out of existence eons ago. But if they were entangled, really entangled, then that connection might still echo across time and space, not as a signal you can read, or a feeling you can point to, but as a silent thread in the underlying pattern of the cosmos. It sounds like poetry, but it's grounded in physics, in equations that don't flinch, in experiments that repeat again and again, always pointing to the same eerie truth. The universe is not made of separate parts. It only looks that way, which brings us back to the top quark. Why does it matter that this particular particle, so massive and short-lived, can be entangled? Because it suggests that entanglement isn't just a fragile feature of tiny, delicate systems carefully protected in labs. It's robust. It can survive even in the most extreme conditions, inside a particle accelerator, in the chaos of high-energy collisions, in the heart of matter itself. It means entanglement might not be the exception. It might be the rule. And if that's true, then the universe isn't a machine full of disconnected parts. It's a kind of unified song, with notes that resonate together across impossible distances, not because they're communicating, but because they were never truly separate to begin with. This forces a shift, not just in physics, but in how we think about being, about connection, about meaning. If particles can remain entangled across space, then maybe the story of the universe is not one of fragmentation, but of relationship. Maybe the deepest truth is not that we are alone, but that we are linked to each other, to the stars, to the very moment of creation. Of course, physicists will remind you, entanglement doesn't mean telepathy. It doesn't mean fate. It doesn't mean your atoms are whispering secrets to the cosmos. But isn't there something beautiful, even necessary, about the idea that the smallest parts of reality are not isolated, that the basic units of existence are bound together, invisibly, inexplicably? In a time when we often feel divided, this ancient feature of nature seems to whisper something else. Connection is fundamental. Distance is an illusion. Separation is not as absolute as it seems. Entanglement in this sense becomes more than a technical phenomenon. It becomes a metaphor, and maybe more than a metaphor, for how the universe holds itself together, for how something can be many and still one. So the next time you look up at the night sky and wonder what might be out there, remember, something out there might still be tangled up with something in here, and not just symbolically, literally. You are not a separate island floating in a vast, uncaring sea. You are part of the sea itself, a wave in a cosmic field, rising and falling with all the others. Even the most fleeting particles, top quarks that live and die in less than the blink of an eye, don't escape this law of connection. They're born together, they move apart, but somehow they remain as one. So maybe the real mystery isn't how entanglement works. Maybe the mystery is why it ever stops, if it stops at all. So, are quarks even real? It's a strange question to ask about something so foundational. Quarks are supposed to be the building blocks of matter, the things inside the protons and neutrons that make up atoms, that make up us. But here's the catch. No one has ever actually seen a quark. Not directly, not in a microscope, not even in the way we've seen electrons leave trails in cloud chambers or photons light up detectors. Quarks don't show up like that. They can't be plucked from a proton and placed under a lens. You can't scoop one out and hold it still. In fact, you can't isolate a quark at all. The moment you try to pull one away from its partners, the energy you put in just conjures up more particles, more quark pairs, like a magician's endless scarf. They're always in groups, always hidden, always just out of reach. So again, are they real? It depends on what you mean by real. If by real you mean tangible, something you can point to and say, there it is, then quarks challenge that definition completely. They are the ghost architects of the visible world, not things we've seen, but things we've inferred. Their fingerprints are everywhere, but the hands themselves never appear. But that doesn't mean they're made up. The universe whispers their name through patterns too precise to ignore. In particle accelerators, we smash protons together at near light speeds and watch as a zoo of other particles emerges. The ways those particles behave, the energies they carry, the directions they scatter, all of it points to the existence of something inside, something smaller, something that was always there, but never alone. And not just one kind of quark. 6 flavors, as physicists poetically call them. Up, down, charm, strange, top and bottom. Each with its own mass, its own behavior, its own tiny quirks. They combine in specific ways to form protons and neutrons, which in turn make the nuclei of atoms. Without them, the whole structure of matter collapses. No chemistry, no stars, no life. But the fact that we can't isolate a quark means we're left in a strange, in-between place. They are at once essential and unknowable, indispensable but untouchable. So we're forced to consider a deeper kind of reality, a layer beneath the physical, where things don't have to be seen to be true. Maybe it's time we let go of the idea that real things must be visible, stable, or permanent. Reality, it turns out, isn't made of stuff in the way we were taught as kids. It's not built from hard, little billiard balls bouncing around in space. The deeper we look, the fuzzier the concept of thingness becomes. Quarks aren't little marbles. They're better described as disturbances, ripples in invisible fields, not objects, but events, temporary, conditional, relational. They exist not in isolation, but in interaction. This is a hard pill to swallow. We evolved to navigate a world of objects, rocks, trees, other people. Our senses are tuned to surfaces and solids. But the universe doesn't care about our intuitions. It doesn't owe us clarity. And at the deepest level, it seems to be built not of things, but of relationships between things. Quarks are real in the way gravity is real, in the way time is real. You don't see time, but you feel its passing. You don't see gravity, but it bends the path of your every step. Quarks are like that. You never see them directly, but you live inside their consequences. Their behavior shapes the world we take for granted. Why are atoms stable? Why do protons and neutrons have mass? Why does the sun burn? Why is there a periodic table? It all traces back to quarks and the strong force that binds them. They are the hidden gears behind the machinery of matter. And that brings us to something bigger. What do we mean by existence, really? We like to think of reality as made of things, but quarks force us to consider that maybe reality is made of rules, patterns, laws, symmetries. Maybe the universe isn't a collection of objects, but a kind of music, mathematical harmonies playing out in space and time. In that music, quarks are notes. They matter not because you can isolate them, but because the melody doesn't work without them. There's a beauty to that, a kind of humility. We don't need to see everything to know it's real. Some truths leave traces instead of faces, like the wind shaping sand dunes, or dark matter sculpting galaxies, or quarks holding together the atoms in your hands. And it gets even stranger. The very theory that describes quarks, quantum chromodynamics, is so complex that we can't even solve it exactly in most cases. We use approximations, simulations, clever tricks. We rely on massive supercomputers to guess at answers that the equations stubbornly hide. It's a reminder that nature is not obligated to be simple, just comprehensible enough that we can glimpse it, but never grasp it fully. That's where things get philosophical. Do quarks exist only in our theories? Or do they exist out there, independent of us? Are they discoveries or inventions that work? If a thing can't be isolated, if it can't be directly observed, but it perfectly predicts every outcome we measure, does that make it real? Some would say no, that unless we can touch it, see it, isolate it, it's just an idea. But the world doesn't seem to care about our definitions, and the deeper we dig into the fabric of reality, the more we find concepts that defy the boundaries of language. Maybe real is the wrong question. Maybe what matters is necessary. Quarks are necessary. Without them, the structure of matter makes no sense. The sun wouldn't shine, the stars wouldn't fuse, The atoms in your body wouldn't hold together. The table in front of you would dissolve. The universe as we know it wouldn't work. So even if we never see a quark, we see because of them. We exist because they do. It's like trying to argue whether the soul is real. If it can't be weighed or measured, does that mean it's imaginary? Or does it mean we're asking the wrong kind of question? Some truths live outside the spotlight. Some realities don't want to be caught, only understood. Quarks remind us that the most important things often hide behind layers of indirection. They're not center stage. They're the stage itself. They are the logic of existence, embedded in code too deep for our eyes. And maybe that's the truest kind of real there is. Quarks aren't what we thought matter would be. They're not little dots floating in space. They're not solid, not stable, not even separable. You can't scoop one out, look at it under a microscope and say, there it is. A quark alone simply doesn't exist. The moment you try to isolate it, it vanishes into something else. Like a word that only makes sense in a sentence, it needs its companions to mean anything at all. They're more like notes in a chord, alive only in relation to others, or ripples in a dance too fast for us to see, yet still shaping everything. Without quarks, there are no protons. Without protons, no atoms. Without atoms, no stars, no planets, no people, no you. But here's the strange part. They aren't really things, not in the way we usually think of things. They're disturbances in invisible fields, events, happenings, like a spark that flares into being, changes the world around it, and disappears again, only to reappear somewhere else, never still, never solitary. And yet somehow, these flickers are the glue of the universe. They hold everything together. The very fabric of matter depends on them playing their endless, restless game. That alone is hard enough to grasp. But then we look inward. Because bizarre as it sounds, that's what you are made of. You're built from this. Not stone or steel or anything solid in the usual sense. You're made of movement, of interactions, of fleeting events that never settle, but somehow cohere. Your body, your thoughts, your memories, all of it emerges from a storm of particles that only make sense in patterns, in relationships, in context. And this brings us to something quietly profound. Maybe reality itself isn't built from things, but from connections. Maybe what's real isn't what you can hold in your hand, but what persists across time through interaction, through resonance, through meaning. It turns everything upside down. We like to think of ourselves as individuals, separate, independent. But if quarks teach us anything, it's that nothing exists in isolation. Not truly. Even the smallest building blocks of matter are bound to each other by forces that can't be broken. Try to split them apart, and they create more of themselves just to keep the connection going. That's how strong the universe's need for relationship is. Maybe that's true for us too. Maybe you're not real because you're made of some fundamental stuff. Maybe you're real because your pattern holds, because you influence others, because you're part of something larger, just like quarks are part of protons, part of atoms, part of stars, part of us. The deepest truth quarks whisper isn't about physics. It's about existence. It's about how even the smallest, most elusive entities matter when they're part of a greater whole. That might be what it means to be anything at all, to belong, to resonate, to be part of a song that began before you and continues long after and still needs your voice to be complete. So maybe you are like a quark, fleeting, mysterious, impossible to pin down, but vital. You shape the world around you, even if you never quite stand still. You affect others, you leave echoes, and in doing so, you become something greater than the sum of your parts. You are not a thing, you are a pattern that holds. And maybe that's the most beautiful kind of real there is. If you found this journey into the world of quarks mind-boggling, drop a comment below and share what fascinates you the most about these mysterious particles. And if you haven't already, don't forget to like the video and subscribe to the channel so you don't miss out on our next deep dive into the mysteries of the universe. Thanks for watching, and keep questioning everything. because the universe is far stranger than we can imagine.